All right, let's talk about sports science from a biomechanics perspective. So, what is biomechanics? If you hear that term or if you've gone into your biomechanics class on the first day, what is it that you were thinking it was going to be about? And maybe what was it that it ended up about? But typically, people think about biomechanics, they think of things like it's about technique, it's about forces, kinetics, it's about movement or kinematics. And it's also math and it's also physics. And it's using those tools, math and physics, to understand movement. Now, in biomechanics, in our area, in the Department of Kinesiology and Nutrition Sciences, we're typically dealing with humans as our focus. And so we typically want to understand human movement. From a pure definition of biomechanics, this is as good as any, a science which investigates motion, kinematics, and the action of forces, internal and external to the person in our example, including statics, dynamics, kinematics, kinetics that occur during the actions performed by a living organism. For example, a human being. I have friends that do biomechanics of goats walking or elephants walking or what have you. That's comparative biomechanics. Different line of work, but still biomechanics. What I typically tell someone on the street, if they ask me, what is biomechanics? I typically just say, oh, it's the physics of sport. That's a nice way to sort of encapsulate what biomechanics is about. We're going to use some physics, we're going to do some math, and we're going to apply it to sport or human movement. So let's look at sports science from a biomechanics perspective. Typically, when we think of a biomechanist as part of a sports science team or as a sports scientist, we're talking about someone who's going to be involved heavily with measurements of kinematics and kinetics, data processing of whatever tool is being used, how to process the information, to ultimately give a report back to someone, whether that be an athlete, a coach, a practitioner. And also, a biomechanist is going to be thought of as doing some type of movement analysis or some type of description of groups of movements in order to help with coaching. Now, what is important is when you are working as a biomechanist as part of a research team or working as a sports scientist using biomechanical tools, we got to know the terminology. This is so critical. And so when I teach courses like undergraduate biomechanics or graduate biomechanics, or even classes like this that you're watching the video for, it is so important to know terms. You need to know the definitions of terms. You need to know the equations of terms, if there is an equation, and you need to know units of terms that where it's appropriate. And so a lot of this is rote memorization, but you need to know this stuff to talk about before you can start applying those terms like force, pressure, work, energy, power, what have you. Those terms, we need to know definitions, we need to know equations, we need to know units, and then we can start trying to understand how to quantify those terms and then use them in helping an athlete perform. So as I said, biomechanists are very involved with the data collection and in the data processing process. And what's really important when a biomechanist gets pulled into a sports science team or starts to work with an athlete, a coach, a practitioner, what have you, what's really important is first and foremost to know, why are we testing? What do we want to know? Because that is going to drive some decisions about what tools we pick, what context we collect data in, how we process the data, and what information we're ultimately trying to get. It is so easy to collect bad data. And so I think of this as sort of a circular process when we start collecting data. So what do we want to know? And a lot of times as a biomechanist, we'll sit down with a coach, we'll sit down with an athlete, team physician, other sports science team member, nutritionist, strength and conditioning, whatever it is, and try to have a conversation about what is it that we want to know about an athlete or team. And then it's also nice to have, well, what do you think? And this is, in essence, in the scientific world, it's a hypothesis. It's a statement we believe to be true based upon what we know. Once we have these two things sort of hammered out, then we have to pick the right tools. As a biomechanist, there's a lot of different tools. So we're going to focus on kinetic tools where we're trying to quantify forces. Are we going to focus on kinematic tools where we're trying to understand the kinematics and movements? Or maybe we're looking at muscle activity, or maybe we're doing something about equipment evaluation, and we want to use the right tools to evaluate the equipment. Once we have the right tools picked out, then we go ahead and we do some measurements. And again, we have to even design the context under which the measurements are being conducted. For example, if we're interested in jumping, do we have an overhead goal? Do we not have an overhead goal? Are we focused on dunking a basketball, or are we just jumping for the sake of jumping? Once we have that all done and we've collected the data, then we have the process of processing the data. It's easy to collect a lot of information in a very short period of time. A lot of our instruments will collect 1,000 data points per second. And then you have to take those 1,000 data points per second and then reduce them in some way to give some meaningful data point to discuss. And so that's where we start doing an analysis. We try to be objective with our analysis as well. And then you stop and say, wait, was I right? You know, going back to one of the earlier questions here in this sort of circular model. Was I right? And if I was right, well, what does that tell me, and what do I now need to know? If I was wrong, well, why was I wrong, and what do I need to do next? And so you go right back to the beginning. What do you want to know? What do you think? Now that you've done something, well, pick the right tools. Maybe it's a different tool. Measure again, maybe under a different context. Process the data. Were you right? If not, and so this was a very circular process. And along the way, the idea is that as you do this circular process, you're generating knowledge. And that's really important. We're trying to understand something that will ultimately help the athlete, the person who's doing whatever it is that we're working with. And so this is an iterative process. Unfortunately, a lot of times what happens is a biomechanist may be pulled in on the measurement phase, and they don't know, well, what do we want to know? They don't know, well, what do we think is going on? They may not have even been involved with selecting the right tools, but you're asked to measure. And that's really hard to step in to this process at this point, or maybe at this point, or this point. It's not easy to come in at these different phases of this process. And so really it is important as a biomechanist to be pulled into this sports science model early on, so you can pick the right tools, you can design the right type of experiment or context under which data are processed, you can process the data appropriately, and then give the coaches, the athlete, the practitioner, whomever, the information that will help them move forward. Yeah, this is where you want to start. Sorry, emphasizing that red arrow. This is where you want to get involved. So as a biomechanist, what you may also be doing is a qualitative analysis. You're looking at the quality of data. You're looking at the quality of movement. Sorry, I shouldn't have said quality of data. That gets in the quantitative part. But you're looking at the quality of movement. And when you do a quantitative analysis, there are ways that you take a movement and then you start creating phases or groups of movements. You start identifying discrete events that separate out phases. And you really need to know your functional anatomy and your movement terminology when you are doing this type of phase. And this is such an important part of the scientific process, because really step one of the scientific process is observation. You have to view something a lot. So if you're trying to help someone jump higher, you need to watch a lot of jumps. You need to watch a lot of different techniques of jumping. You need to understand different phases of jumping. In this case, this is a lacrosse shot. And as a biomechanist, got pulled into a project and said, what's the best way to shoot the lacrosse ball? I've got a whole presentation on that. It's a complicated question to answer because there's all different ways to shoot the lacrosse ball, all different ways of shooting the stick, and overhand, underhand, sidearm, what have you, quick stick, all different contexts that the shots happen in. But we started with one type of shot, and we identified phases and discrete events in order to then go back and say, okay, now we want to do a quantitative analysis, but only in a couple of these phases. We're not too concerned about what's happening back here. We're more interested in this phase right here. And so doing a qualitative analysis is really a really good skill to have, and an important step in doing a biomechanics approach to sports science. Quantitatively, when we start trying to collect data, there's a number of things that we need to concern ourselves with. Well, we need to know, are we going to collect kinetic data? Are we going to collect kinematic data? Are we going to look at muscle activity data? Are we going to look at physiological data? What is the information that we want? And then we need to pick the right tools. And we actually wrote a paper on this, dealing with portable equipment that we can take into doing circus maneuvers and quantify circus maneuvers, and trying to identify what's the right way to pick the right tool for the right act, or that the person's doing, whether it's a trampoline, or whether it's a steer wheel, or whether it's some other type of movement that's involved in a circus type of performance. When we start looking at the collection process, there's a lot of details that we need to know about how the tools work. We need to know the right sample rate, or we need to know what the sample rate is of a lot of tools. And this is a critical point. In a subsequent class where I go into sport performance testing, we actually will spend more time on this slide in particular, where we start looking at the different sample rates that we can set tools to. Are we sampling data at 1 data point per second, 50 data points per second, 100, 200, 500, 1,000, or faster? We need to know that, and there's a reason for why we set a sample rate the way we set it. Obviously, the bigger the sample rate, the more data we have, the more memory that we're actually storing on a computer. And so we do need to be cognizant of the limitation of our data acquisition systems as well. For validity, we need to make sure that the tools we're picking measure what we are expecting them to measure. If we're interested in measuring jump height, we need to pick tools that are valid in measuring jump height. It measures exactly what it's supposed to measure. Reliability, we also need to make sure that our tools are reliable. That is, if we measure something today, we can come back and do the same measurement tomorrow and we'll get the same thing, and the next day, and so forth. And this becomes really important in sports science, because a lot of times we do athlete performance testing at the beginning or preseason, at the beginning of a season, at the midpoint of the season, and at the end point of the season. We need to be confident that the tools that we're using are reliable and are measuring the same thing at each point. And that way, when we go and look at, well, mid-season, boy, the jump height's quite different than the beginning of the season. What's going on? Maybe it's higher, maybe it's lower. Well, we need to rule out that our tool did not measure reliably, that our tool was set wrong, or was not consistently measuring jump height so that we can attribute the change in jump height to the person or something that's happened. So validity, accuracy of the data, it's measuring what we believe it's supposed to be measuring, and reliability, are we getting consistent measurements over time? So now we move on to data processing. We've collected a lot of data. Boy, we can collect a lot of data in biomechanics. Here's some data that this is whatever period of time. This is thousands of data points. But what we need to do is we need to take all those data points and reduce them to some variable that we're interested in talking about. Average electromyography, average muscle activity, average core temperature. what peak maximum force, whatever it is, impulse. Whatever it is that we're interested in, we need to take all the data points that we collected and reduce them. In the laboratory, when we're doing research, we typically write our own programs to process raw data. That means whatever the instrument recorded, we get the data before any processing steps happen, and we're getting raw data. Once we have that raw data, then we process the data where we look at the quality of the signal, and we try to rule out any noise in the signal. So a lot of times we might be looking at muscle activity and our sensors start moving and they're not actually collecting muscle activity, they're actually collecting movement, and we call that movement artifact. We get electronic noise. We're bombarded with, this electrical wilderness that we live in, and we need to make sure that we're not accidentally measuring just this electronic noise that we're picking up in our environment. And so we have the tools that we use to process the data. And when we're doing a research project, it's very critical that as researchers that we know every step involved with taking raw data and reducing it to some type of smooth or processed data. Unfortunately, a lot of tools that we have access to for field testing, where the data are very or the instruments are very portable, a lot of times the equipment comes with proprietary software that processes the data in some way. Many times the manufacturers do not disclose what steps of processing they employ, so that the data that you're looking at, you may not know what actually happened in the processing step to get the data that you're looking at on your phone or your computer, whatever it is. And so this is something that a biomechanist, we really need to be very aware of when we're working with and selecting with different tools, that we know what stage of data we're working with. Is it highly processed data? And we don't have access to the raw data, or can we get the raw data and process it in steps that we want to process and that we're then aware of? Because it will ultimately impact the quality of the data that we actually analyze. And it is important to know your key variables that you're looking for. I mentioned jump height. Well, do we just want to know jump height? Or do we want to know the impulse that generates a takeoff velocity that yields a jump height? Or do we want to know what's happening when the person's landing and the impact forces upon landing? We didn't know the right variable to sort of zero in on when we do our data processing. And if we're working in the research world, we'll start using terms like dependent variables and independent variables. And dependent variables are what we're trying to analyze: jump height, impulse, peak impact force. All right, those are the things that we're measuring, and we want to analyze those specific variables. Independent variables may be something that we're manipulating. Maybe we jump in different shoes, or we use different jump styles, or maybe we're looking at jump over different points of a season. In that case, time for the season, that would be an independent variable. It's what we're manipulating. And then we would compare jump heights over preseason, beginning of the season, mid-season, postseason, and we would do an analysis that way. Our dependent variable would be jump height, or independent variable would be time. And so this is an important component to know as a biomechanist in sports science, because you dive into literature, you need to understand when authors are talking about dependent variables and independent variables. Okay, so once you have your data collected, once you have your data processed, you now need to prepare a report. It's critical to know who are you preparing the report for. If, as I just talked about, if you're going to publish data in a peer-reviewed journal, well, you're writing that report for other scientists. And you need to write that paper in that report in that context. If you're giving a report to a coach, that may look quite different than what you would submit for a peer-reviewed journal. If you're giving a report to an athlete, if you're giving a report to a team physician, a sport medicine doc, or physical therapist, or some other practitioner, when you're giving a report, you have to know who you're giving it to, and then you need to give the right amount of information and right quality of information. Well, you always need to be quality, but the right amount of information and the right type of information. And we need to be careful about paralysis by analysis. And what I mean by that is it's so easy to get down into the granular level of details of data analysis. This is very easy to do, especially as a biomechanist. I mean, we start, getting into the weeds of different types of smoothing routines or different type of algorithms to process data. But you can ultimately get paralyzed by all these different types of analyses. And so you do need to be careful that when you're delivering a report, you often want to make sure that you're providing some type of actionable items that the coach, the athlete, the practitioner, whomever it is that you're working with, can then use. And you do need to think about data visualization. This is the way of illustrating all the data points that you collect, either graphically or tabular numbers presenting actual values, what have you. But you really do need to consider who you're presenting to. You need to present it, how you're going to present, and you need to be careful of not paralyze everyone or anyone by over-analysis. How do you do all this? Well, you got to form a great research team. When you do athlete performance testing or work in the sports science environment, you really want to have a wide range of people who are helping you collect data, process data, ask questions, and then redoing the system. It's iterative. And you got to have people who are able to adequately operate the equipment and provide instructions to the athletes in terms of doing whatever the test is that you're doing. And there's so many different tests that you need so many different people. And when we go and do a combine type test, we like to have an army of students going out and working with the athletes. And we always train our people who are going out on their combine events. We go through, well, what are the instructions that you give someone? How do you operate the equipment? How do you save the data? What information do you give back to the athlete immediately, if anything? And there are so many different types of tests, from sprinting, shuttle runs, to unique string testing for the neck in this case, vertical jumping using a jump mat or force platforms, doing string testing, medicine ball throwing, vertical jump, isometric pole tests, broad jumps, squat tests, what have you. There's so many different types of tests that it is important to be really cognizant of how the instructions to the athlete may ultimately influence the quality of your athlete performance testing protocols. And I've used this model in other presentations. I just want to draw your attention to where we are as a biomechanist. This model, I always talk about human performance as a function of having potential chemical energy, glucose, carbohydrates, fats, and proteins, having those in the body, transforming that potential energy either aerobically or anaerobically, and generating mechanical energy, applying a force over some distance. And when we're doing our test, if we're asked to even come up with a test, we have to make sure that we are picking the tools to test the right energy system, or that we're understanding the energy systems that are taxed by certain tests and what have you. But ultimately in biomechanics, you're more focused in this area, a little bit in this green area, maybe a little bit coming over here in this section here. But again, this speaks to the point that to understand human performance, you got to have a wide range of knowledge, and you have to have a wide range of expertise. And in this model of kinesiology, where we're ultimately understanding human performance, again, I've got a separate presentation on this whole model. Human performance is nothing more than a bunch of movements. We need to know our functional anatomy. That works into our qualitative analysis. Movements are described through displacements in time. That's kinematics. This is biomechanics world. How does a displacement in time happen? Well, it happens through forces, both internal from muscles and external, something pushing outside the body. That's our kinetics. That's biomechanics. We need to know Newton's laws of motion. In muscles, if we're dealing with internal forces, we need to know how muscles generate forces. That's physiology, but this is where biomechanics and physiology cross over quite well with trying to understand muscle forces. And then the brain tells the muscles what to do. And what the brain is doing is ultimately influenced by the environment. This could be everything from wind, air, temperature, humidity, but it could also be psychological environment, performing in front of a crowd or a pressure point that you need to win or what have you. And so in biomechanics, we are more in this region here, but again, we have to know the whole range of this model and all these different areas to understand human performance. So let me sort of wrap up with these last two slides, or last couple slides. Sports science from a biomechanics perspective. There's so many different tools that are available to us to be able to measure out in the real world. Portability is fantastic, but it does lead to other questions about validity of tools, reliability of tools. We need to know the accuracy of the tools. We need to know how tools perform, how they collect data, how we can get the raw data, how we can process the data. So it's an exciting time in sports science, especially from biomechanics, but it's a challenging time as well because it's easy to collect bad data. So we want to ultimately, as sports scientists in the biomechanics perspective, we want to take all these tools, all these different data points, we want to apply it to a sport, and we ultimately want to take all this information and we want to generate knowledge. That's our goal. All right, thanks so much. I hope this is helpful. Have a great rest of the day.